There are many results, many lemmas relating to the probability or the sum of probabilities or some convergence in the area of probability theory. The basic and one of the most important such result is known as Borel Cantelli Lemma. This is actually due to joint two probabilists, Borel and Cantelli. Today we are going to state this Borel Cantelli Lemma, its importance, we will mention its importance and the rigorous proof of Borel Cantelli Lemma. Now it is important to mention in this context that Borel Cantelli Lemma somewhat one way result. So the natural question is, can we get both way, that is, if something holds, if and only if another thing holds, something like that? The answer is yes, and to this end we can extend this Borel Cantelli Lemma to prove or to mention one more important law or result, which is known as Borel 0-1 law. Now in this context, while proving this Borel 0-1 law or while moving from Borel Cantelli Lemma to Borel 0-1 law, we need one important concept which we have already discussed, that is called independence. So from Borel Cantelli Lemma, if we want to move on to Borel 0-1 law, we need the concept of independence or independence of events. So with this prelude, I would like to discuss now Borel Cantelli Lemma and Borel 0-1 law in a very rigorous way along with the proofs. So let us start our discussion with the famous Borel Cantelli Lemma. Before introducing the lemma, let me tell you, this is the picture of Borel, the famous mathematician, and the right side is the picture of Cantelli. So these two actually developed this lemma, which is a landmark in probability theory. Now what is this famous Borel Cantelli lemma? Before that, let me introduce one definition which I think we have already studied, but let us do a small recap. Suppose n equals to 1 to n be a sequence of sets. Then we say n occurs infinitely often, or I full stop O full stop, infinitely often means lim sup of an. Lim sup of an means first consider union of n equals to m to infinity, and then consider intersection of all such events, that is m equals to m equals to 1 to infinity. So intersection m equals to 1 to infinity of union n equals to m to infinity of an is known as lim sup of an, or an occurs infinitely often. Now we consider that we will prove this Borel Cantelli Lemma, which is a very important result in probability theory, and many results mostly relating to convergence can be proved using this Borel Cantelli Lemma. So what is this Borel Cantelli Lemma? Let us consider a probability space as usual, where omega is the sample space of the whole space, script f is the sigma field generated by the class of subsets of omega, and capital P is the probability function defined on this omega and script f. So this we call the probability space. Now consider a sequence of events an, that means for each n equals to 1, 2, 3 and so on, an belongs to script f. Now we are interested to find out what would be the probability that an occurs infinitely often, that means probability of lim sup of an. Now this Borel Cantelli Lemma states that if summation of p an, that is n equals to 1 to infinity, summation of p of an, probability of an less than infinity, then probability an occurs infinitely often is actually 0. So this is a very interesting and important result, as I have already mentioned. So let us try to prove this Borel Cantelli Lemma. Now if we go step by step, the proof is basically very simple, although it involves couple of complicated notations, but if we go through this step by step, it looks very simple. Now what is the definition that an occurs infinitely often? As we have already mentioned, this is nothing but intersection m equals to 1 to infinity of union n equals to m to infinity of an. Now take probability on both sides. That means probability n occurs infinitely often is nothing but probability of intersection m equals to 1 to infinity union n equals to m to infinity of an. Let us consider this as equation 1. Let us denote, instead of considering this whole complicated things, let us denote the last part, that is k equals to n to infinity as bn. So naturally we are taking some k equals to n to infinity, so it depends on n. So we can consider this union of k equals to n to infinity as a particular set that is indexed by n. So we call this as bn. Clearly bn is decreasing in n, that means as n increases bn decreases. So we can immediately say that the limit exists, then limit n goes to infinity, probability of bn equals to probability of intersection n equals to 1 to infinity bn. Now bn decreases with n, and now bn decreases with the intersection of bn. Bn decreases to intersection of bn, that is n equals to 1 to infinity. So limit of probability of bn is nothing but probability of intersection bn n equals to 1 to infinity. Now let us put only for the sake of clarity what is bn. Bn I can immediately write as intersection m equals to 1 to infinity union n equals to m to infinity of an. So probability an occurs infinitely often is nothing but, now remember the right side is nothing but probability an occurs infinitely often. So we can immediately write probability an occurs infinitely often equals to limit as n goes to infinity of probability of bn, which is equals to limit as n goes to infinity probability of union of k equals to n to infinity. Now we know that union can be upper bound, can be bounded above by summation, so it is less than equals to limit n goes to infinity k equals to n to infinity probability of ak. That means we say that we immediately get that probability an occurs infinitely often is less than equals to limit n goes to infinity k equals to summation k equals to n to infinity probability of ak. Let us call this as equation, rather in equation 2. Now there is one given condition in Borel Cantelli lemma. That condition says that the summation k equals to 1 to infinity probability of ak is less than infinity. That means this is actually convergent. So we can always find some n such that means the given condition summation k equals to 1 to infinity probability of ak less than infinity implies that summation k equals to n to infinity probability of ak less than epsilon for n greater than equals to n naught epsilon. This means that for every epsilon greater than 0 we can always find an n naught epsilon such that whenever n is greater than or equals to n naught epsilon we have summation probability of ak sum over k equals to n to infinity is less than epsilon. That means the upper tail part should be arbitrarily small, in fact smaller than any arbitrary small positive quantity. Now if we apply this condition in equation 2 we immediately get probability an occurs infinitely often is just less than epsilon for every epsilon greater than 0. Now this is true for every epsilon greater than 0. That will immediately implies that probability an occurs infinitely often is basically 0. Now the question naturally comes, although we have proved this Borel Cantelli lemma under a particular condition, now the question naturally comes, is the converse true? What should be the answer? Answer is yes, but under a particular condition. Now what is this condition? And the condition is nothing but this: there is a particular condition, and putting that particular condition, when we explore the converse, which we will prove that to be true, or that actually gives us another result, which is known as the famous Borel 0-1 law. So let us now discuss this Borel 0-1 law. Again, to start with, we have a probability space omega, script f and p, where P is the probability function defined on the sample space omega and the script f, which is the sigma field generated by the class of subsets of omega. And here An we have already considered in Borel Cantelli lemma, An which is a sequence of events, sequence of sets belonging to script f. Here we impose additional restriction that let An be a sequence of independent events or independent sets. Then probability of An occurs infinitely often equals to 0 if and only if, that means it's now both ways. So it contains the converse of Borel Cantelli lemma, if and only if summation n equals to 1 to infinity probability of An less than infinity. That means this converse is true when the sequence of events are independent, which immediately implies that probability of lim sup of An equals to 1 if and only if summation probability of n equals to 1 to infinity is equal to infinity. Both way we can write, there is no problem which way we want to write, and we can prove any one of this. Now what is the proof? Again, exactly in the same way as in Borel Cantelli lemma, let us first write down what is the meaning of probability An occurs infinitely often. Now for the moment let us consider, or let us try to prove the second line, which is equivalent to the first line. That is, assume that probability An sum over that n equals to 1 to infinity equals to infinity. Then we use De Morgan's rule and we apply the continuity theorem of measure. Here measure means probability in this case. So let us start with 1 minus probability An occurs infinitely often, which is applying De Morgan's rule. We can immediately write probability of union n equals to 1 to infinity intersection k equals to n to infinity a k complement, which is again equals to limit n goes to infinity probability of intersection k equals to n to infinity a k complement, because we can show that this intersection is a class is actually an increasing function, and so this the limit would be the union. Now this again equals to limit n goes to infinity limit n m goes to infinity k equals to n to m. So we just write the upper limit as m and tending m to infinity of ak complement. Now again applying this, we can take this limit outside. So limit n goes to infinity, limit m goes to infinity, probability intersection k equals to n to m ak complement. Now remember one extra condition that we have imposed in while stating Borel 01 law, that is the condition of independence. Now we know that if ak is a sequence of events which are independent, then ak complement will also be independent. So probability of intersection of ak complement is nothing but product of probability of ak complement product over k equals to n to infinity. Now using a standard inequality we can write immediately this is less than equals to limit n goes to infinity, and putting this m goes to infinity inside we can get this is exponential or e to the power summation probability of ak k equals to n to infinity with a minus sign attached to it. Now naturally the given condition is that summation probability of an equals to infinity, so raised to the power e to the power raised to the power minus infinity, or a very large number, so this goes to actually 0. So what we have is that 1 minus probability of an occurs infinitely often is less than equals to 0. That means probability of an occurs infinitely often is greater than equals to 1, which immediately implies that probability equals to 1, because it cannot be greater than 1. So probability an occurs infinitely often equals to 1 when n is a sequence of independent events. So naturally this proves the converse, and the other part is nothing but the Borel Cantelli lemma, which is indeed true even when they are not independent. So let us consider one small example. For a sequence of random variables xn, there exists a sequence of real numbers an such that xn by an goes to 0 almost surely. Now, let me mention one important thing, that this Borel Cantelli lemma is extremely useful in proving various results related to this convergence or almost sheer convergence in probability theory. So, the proof is extremely simple. Consider yn equals to xn by an such that for every epsilon greater than 0, we can have probability of mod yn greater than epsilon less than equals to 1 by 2 to the power n. We can just choose this as 1 by 2 to the power n only for the simplification in the later stage. So, we know that summation probability of mod yn greater than epsilon, where n equals to 1 to infinity, is less than equals to, that means just take summation over n equals to 1 to infinity on both sides. This is less than equals to summation n equals to 1 to infinity 1 by 2 to the power n, which is indeed a finite quantity which is less than infinity. So, we have the condition that summation probability of some events depending on n is less than infinity. So, naturally we can immediately apply Borel Cantelli lemma to see that probability mod of yn greater than epsilon, this event occurs infinitely often equals to 0. That means now this modulus of yn greater than epsilon, this occurs infinitely often means probability of lim sub, that means actually yn converges to 0 almost surely. So, this is a very simple example where we have used this Borel Cantelli lemma in order to show the convergence almost surely. So, we have seen that there are two important results. One is Borel Cantelli lemma, another is Borel 0-1 law. We have mentioned them, we have stated these results, and also we have given the rigorous proof of these two lemmas and the connection between them. That means when we stated Borel Cantelli lemma, we have asked one question, that whether the converse of this lemma holds true, and the converse is true only when a certain condition holds, that is the condition of independence, which actually leads to Borel 0-1 law. Now, this condition of independence is extremely important, and we have already discussed several definitions, several equivalence between definitions of independence, and now we use that concept in order to prove the Borel 0-1 law. Another important thing is that this law is concerned about the probability of a particular or some kind of limiting event, that is lim sub. So, this gives us an idea that this Borel Cantelli lemma or Borel 0-1 law basically deals with the probability of some kind of limit of events. Limit in many sense might be, but limit of event, and we get some nice results on this limiting events, or rather probability of limiting events. So, this actually gives us the idea that we can probably use these two results in proving many other results in relation to the convergence in probability theory, or rather several convergences, and most importantly almost sheer convergence in probability theory, and we have seen one such example. Later on we will also see some more results and some more examples in relation to this area, where this idea of limit or how to calculate the probability of some limits can be explored.